Hello, my name is Xu Ruoxiao. Now let's take a look at the problem. This problem is a constraint optimization problem which requires us to use the KKT methods to find the maximum value of the given function subject to the following constraints. We begin by reviewing the basic 5 steps of the KKT methods as I show on the screen. Let's begin from step 1. We first construct the Lagrangian function based on the objective function f of xy, the Lagrangian multipliers λ1, 2, 3, and the 3 constraint functions. The resulting Lagrangian function is as follows. Then we will list KKT necessary conditions. Here we consider 4 characteristics: stationarity, prime feasibility, complementary slackness, and dual feasibility. The following are their essential properties. Then we begin to analyze the cases of active constraints. We perform case analysis based on which of the constraints are active. There are 8 possible combinations. In each case, we solve the system of equations to determine the values of x, y, and the corresponding Lagrangian multipliers. Then, we verify whether these values satisfy all KKT necessary conditions. If they do, the point is marked as a candidate solution. Otherwise, it is discarded. For example, in case 1, solving the constraint equations gives us a candidate point, 0, 0. Substituting this into all KKT conditions confirms that it satisfies them, so it is returned. In case 2, only G1 is active, while G2 and G3 are not. Solving the equations yields 3 potential solutions. All 3 satisfy the KKT conditions and are added as candidate points. Using the same approach, we can evaluate cases 3 to 8. The procedures and the results are presented below. In total, 7 candidate points are identified. Their coordinates, function values, and the corresponding active constraints are summarized in the following table. To access local optimality, we apply the second-order conditions. This requires calculating the Hessian matrix of the Lagrangian and evaluating it along the tangent space defined by the active constraints. If the Hessian test is inclusive, for example, if the tangent space is trivial, we use the bordered Hessian matrix to determine definiteness. For point 01, we calculate the Hessian of the Lagrangian and the direction d. Since the tangent direction is 0, the Hessian test cannot be applied. Instead, we compute the bordered Hessian matrix, and since its determinant is positive, we conclude that 01 is a local maximum. For point 10, the Hessian matrix is found to be negative definite, confirming that it is also a local maximizer. Using the same approach for the remaining candidate points, we find that -1, 0 and 1, -0, -1 are local maximizers. The points 1/2 1 over square root of 2 and the point 1/2 -1 over square root of 2 are not local maximizers due to positive definiteness. Point 00 requires special attention. Since none of the constraints are active, the problem reduces to an unconstrained optimization problem. The Hessian determinant is positive, indicating that 00 is a local minimum. Here comes the plot of the level curves of the objective function and the feasible sets defined by the constraints. The contours indicate the horizontal value line of the objective function. The closer to the origin, the smaller the function value. The green region indicates the feasible domain defined by the constraints. The red dots mark the points of local maxima verified by KKT and second-order conditions. Based on the complete analysis, we conclude that the maximum value of the function under the given constraint is 3. This maximum is achieved at the points 1, 0, -1, 0, 0, 1, and 0, -1. That's it. Thank you for your watching.